On acoustics, today's video, I'm going to talk about perforated panels. So please check out the video and check out the description so you can find out more information about this website. So I'm using a website where you can put all the information, and it basically shows absorption curves for different scenarios. So there's different options that I'm going to model. I'm only going to use perforated panels, but of course you can model different scenarios. You can use slotted panels, for instance, or normal broadband absorptions. So I'm going to stick with perforated panels. So I'm going to create 4 scenarios, and I'm basically changing different options. So I'm changing the thickness of the panel, and I'm changing the perforation ratio. So there's lots of information here. For instance, you can change the air temperature of the room, the air pressure. There's a bunch of options which you can choose from for these prediction modules. I usually stick with this one, which is pretty standard and conventional. You can change the angle of incidence. I usually also put 0 degrees on this part, and you can change a bunch of options. I'm just going to do this first prediction using this configuration. So now I'm going to hit calculate, and here we have. So we have basically 4 curves for 4 different scenarios. I'm going to go a little bit downwards. So the first 2 scenarios, which is absorption 1, which is the blue line, and absorption 2, which is the green line, we have basically the same perforation ratio. So we have holes with 8 millimeters spaced 20 millimeters. That's around 13%, 12.5% perforation. I'm assuming that we are using rock wool behind the panel. So I placed 100 millimeters of rock wool, which gives us around this value of flow resistivity. Sorry about that. And what I did first was to change the thickness of the panel. So in one panel I have 12 millimeters, usually of MDF, and on the other panel I have 20 millimeters. So if we look at these 2 lines over here, we basically see that if you increase the thickness of the panel, the peak of the curve goes to the left side of the chart, which means that you peak at a lower frequency. So on this blue line, we are peaking around 550, so 550 hertz. And on the green line, which the panel is thicker, we are peaking at around 400 hertz. So this enables us to change the configuration of the panel and for instance, create a panel that is thicker or thinner according to our specifications and our target frequency. Now, I did a couple of more experiments. So I wanted to show you what happens when we actually decrease the perforation ratio and when we increase the perforation ratio. So these other 2 additional lines, which is absorber 3, the orange line, and absorber 4, which is this yellow line over here. So we have 12 millimeters. So we are comparing these 2 lines with the blue line. So we have 12 millimeters thickness panel, but now we are changing the ratio of the perforation. So on the orange line, we have only 3%, okay? And on the yellow line, we have 28%, of perforation ratio. So what we can see when we compare these three lines, first is that they drastically change the peak where the panels absorb the highest. So on the yellow line, it's absorbing at 1000 Hertz. So we have increased the perforation ratio and we get a higher peak of absorption. If we decrease the perforation ratio, we get a lower peak of absorption. So on this case, it's peaking around 200 Hertz. But there's also a huge difference on these three lines, which is the amount of absorption that is made. So the yellow line, the peak at 1000 Hertz is 0.9 or 19%. The peak on these two curves, but specifically at the blue line, is 0.8 or 80%. And when we decrease drastically the perforation ratio, we get only 60%, 0.6 at the peak frequency. So as you can see, the perforation ratio enables us to shift the peak of the absorption chart, but it also enables us to increase or decrease the absorption. So this is important because we use this information so we can control the reverberation time in a room. And if we have all this information, then we use this in a Excel spreadsheet or in a more advanced prediction model, for instance, using a CAT or Audion. We can actually target our main goal in terms of reverberation, be it in the amount of the decrease that we want to perform, but also respectively in terms of the frequency that we want to absorb. There's more information around here. So, of course, we can also see that the yellow line has a wider curve in terms of the Q value. So the Q value basically translates to how large is our absorption chart in terms of the range of the frequencies that we are absorbing. So, for instance, if we compare these three lines over here, we can see that the yellow line has a much wider range of frequencies than these two lines over here. So this is also important because, especially if we're dealing with large room acoustics and large spaces, most of the absorption at high frequencies is made with the air enclosed in a room. So we might want a panel that is actually more narrow in terms of the frequencies that we are aiming for. Of course, just to say that, of course, all these four configurations, they roll off in terms of the high frequencies, and they all roll off in terms of the low frequencies. But the low frequencies are controlled mostly with the absorption and with the air cavity that you place behind the panel. So what we see here is that in these four configurations, this area over here is drastically different from each panel, but this area over here, it's almost identical because the materials behind the panel are the same. So I placed 100 millimeters of porous absorption behind all these configurations. If I have changes, if I have changed any of these configurations, or if I have added an air cavity behind any of these configurations, it would for sure present a different configuration and different results over this area. But since they are the same, we can see that in this area below 200 Hertz, the panels are more or less identical. They have some changes, but this is not very significant. So where they drastically perform differently from one another is at medium and high frequencies. So of course, I mean, you can do a bunch of options on this kind of situations. You can change different options. You can create different scenarios when, for instance, in one panel you are using absorption, but on the other panel you are using absorption and air cavity, or you can change the specifications of the material behind the panel. So, for instance, you can use rock wool, which would have a higher flow resistivity, but you can use another kind of absorption material. For instance, you can use PET absorption panels, which have a lower resistivity of sound, and of course the results would be different from all this kind of modifications. But on this video, I just wanted to focus on the specifications of the perforations of the panel and the thickness. So I hope you have enjoyed this video, and please stay tuned for more information, and don't forget to subscribe to the channel. Thank you so much.